So it's valid to wonder, how does all this number theory get applied? Well, at least in the scope of cryptography, the RSA encryption-decryption algorithm. RSA stands for the names of the three credited with this algorithm: Rivest, Shamir, and Adelman. And if we recall, the idea here is that Anne has some message that a single value of which we would refer to as a capital P, and what she needs to do is she needs to get that to Bill, and Bill could be a bank. And so in order to transmit sensitive information over the internet, we want to make sure that it's encrypted. So this capital P becomes a new value, capital C, some disguised value. And in order to do that, that is going to be the output of a function, that the function of which is going to be related to this algorithm, that takes in three inputs. First of all, it takes in the value that we want to encrypt. And then we need a public key and an encryption exponent. So this guy here is called the public key, and this is called the encryption exponent. And it's called that because it's an exponent. And then now the C value is what gets transmitted to Bill, to say the bank. So that is received, that value of C is received. And of course, that's not going to do any good because Bill needs to know what was the message that Anne was sending. Well, in order to do that, he has to apply an inverse function to that value of C, along with this value right here. And what this value B is called, this is called Euler's totient. This is otherwise known as a private key. And the reason it's private is because the only person who could open the box that sort of Anne proverbially locks is the person who has the ability to unlock the box. So that's the key that unlocks the box, and only was able to lock the box. And Bill also has this exponent called the decryption exponent that will be needed in order to reverse this process. So let's see how this all works together, and we'll look at a real basic example of this. So the first step is to convert the message to numerical equivalence. The numerical equivalent in this case that we're going to use, we're going to pretend like Anne's the first digit in her credit card number is 8. And then we need to pick these lowercase p and q, not to be confused with the capital P and Q, that are distinct primes. They're very large, ideally. But we're going to make them very, very small because we're going to do this by hand. So little p we'll just say is equal to 5. And maybe I'll give this a little tail to indicate that it's a lowercase. Q we'll just say is 11. And therefore n is 5 times 11, which is 55. Now this value of b takes away 1 unit from each of these two prime numbers and multiplies them together. So this will be 4 and 10 multiplied together, which will give us 40. This value is called Euler's totient. And if you want to read up about what it means, we're not going to go into the theory of this method because there's actually a lot more going on here than meets the eye. We're going to see that it works, that this function, this algorithm, is 1-to-1. So 1-to-1, remember what that means is that for every input, for every plain text, there's only going to be one capital C, one output. And for that one capital C, it's going to link back to a unique input. That's very important, right? Because if Anne transmits 8, but Bill decrypts it, or she encodes 8, but then Bill decrypts the C value into a different P, then we're in trouble. The third step that we need to do here is for the setup, is to choose a positive integer e so that the greatest common divisor between e and Euler's totient is 1. In our case, that's going to be e and 40. So there's lots of different choices you can make here. I'm just going to go with a real simple one here. I'm going to pick e equals 9, and hopefully you can see that there are no factors that 40 and 9 share in common that aren't 1. So 9 is divisible by 3 and 9 and 1, but 40 is not divisible by 3 or 9. Okay, so we have to make sure that's an important step here. They have to be relatively prime. Okay, so now call each coded letter plain text. So if you were taking an alphabetic letter, like let's say this wasn't a credit card number, but it was a word, you could convert the letters into numbers simply by describing the letter's position in the alphabet. So A would be encoded as 1, or you would do some sort of shift or some sort of, there are different techniques for doing that. But in this case, we already have a plain text value. We're gonna say that capital P is 8, first number of the credit card, and now we need to code that into a C value. Now, we're not going to use the subscripts here just because we only have one value, so we don't need to distinguish among them. So in our case, we need to compute the ciphertext according to this process. C is going to be the remainder of our p-value, which is 8, raised to the encryption exponent, which is 9, mod n, which is 55, based on the primes that we picked. This all plays together to ensure that this function is one-to-one. Now, this requires regular exponentiation, so the way we would start this is we would say, well, 8 to the first mod 55. 55 doesn't go into 8, so it leaves the remainder of 8. And then we'd go 8 squared mod 55, up until we just barely exceed 8 to the 9th, or we're just slightly under it, to where we then double our exponent again, we exceed 9. So we'll actually end up going to 8. 8 squared is its remainder of 8 mod 55 is just 8, so nothing interesting here. This algorithm doesn't help us in this line, but 64 mod 55 is 9. So if I have 64 cupcakes, I put 55 in a box, I'll have 9 left over. Now we do 8 to the 4th mod 55. And that's congruent to the remainder of 8 squared, which is 9 times 9 mod 55. And that's 80. 81 mod 55 is going to be 26. And finally, 8 to the 8th, because notice that if we double 8, we get 16, and that's bigger than the exponent that we're trying to achieve. So 8 to the 8th would be the remainder of 8 to the 4th mod 55, which is 26. And since there's two factors of 8 to the 4th, it's 26 times 26 mod 55. Now, 26 squared comes out to 676. 55 goes into that 12 times. 676 minus 12 times 55 ought to give me the remainder, which is 16. Perfect. Okay, so now to construct 8 to the 9th, we need to grab the corresponding remainders that will construct that number. So 8 to the 9th, we'll notice, is 8 to the 8th times 8 to the 1st. So this equals 8 to the 8th times 8 to the 1st mod 55, and that is congruent to the remainder of 8 to the 8th, which is 16, times 8 to the 1st, which is, its remainder is just 8 mod 55. And so if we do 16 times 8, we get 128. 55 will go into that twice, and that will leave us, let's see, 128 minus 2 times 55 gives us a remainder of 18. So my friends, that means that C is equal to 18, and that is the message that is going to get transmitted to Bill. He's going to receive that. So what does Bill do with it? Well, Bill needs to decipher it. He needs to decrypt, in other words, this value, because what he gets is he sees C is equal to 18, but he doesn't know what message Anne intended to send. So if Bill is a online vendor or something, or he'll need to decrypt that value to figure out, well, what's that credit card digit? And so to do this, we need to find the decryption exponent. Again, very kind of esoteric seeming, but there's just a lot of theory behind this. Find a value of D, a non-negative, smallest non-negative, ideally. It doesn't have to be the smallest, just the smallest makes the math a little bit easier, so that E times D is congruent to 1 mod B. Now this translates, if you convert this into what this means as an equation, it means that ED plus KB is equal to 1. Now recall that the GCD between E and B, our value of E, remember, was 9, and B was equal to 40. And notice that this value, this is the GCD. And so to solve this, really what we need to do is we need to find the value of D. So if we wrote this in terms of the extended Euclidean algorithm, it would be D times E, which is D times 9, plus something times B has to equal 1. Now we don't really care about the K. The K is not important, but it's going to emerge as a result of doing the extended Euclidean algorithm. So the way, remember, we set this up is we say, all right, well, 40, the bigger of the two numbers, how many times does 9 go into that? 9 times what? And what remainder does it leave? Well, 9 goes into 40 4 times. That's 36. That leaves 4 units left over. Now we carry 9 and 4 down. That's this 9 and this 4. 4 goes into 9 twice, leaves a remainder of 1. And now we carry down this 4 and this 1. And we get 9, I'm sorry, not 9. 4 is equal to 1 times what? Well, 1 goes into 4 4 times, leaves a remainder of 0. So there's our GCD. And thankfully, this only involves 2 lines, which is kind of nice. So remember, the way we like to code this up is we like to say, let's call 40. Let's refer to that as what it is symbolically. It's B. And this 9 right here, this 9 is E. So this 9 over here, it's just the carry down of this 9, and that's still E. And remember, this 4 is the carry down, right? So we're going to actually need to make that substitution. So expressing the remainder in each line as a combination of B and E will give us 40 minus E times 4. Or 40, I'm sorry, we don't want to use 40, we want to use B. B minus 4E. Okay, so all I did was just subtract it over the 4E. B minus 4E gives us 4. And double check it, make sure it works out. In the second line, we again solve for the remainder. 1 equals E minus 4 times 2. Or 2 times 4, doesn't matter. So notice that this 4 right here is the same as this 4 right here, and that's where we make our substitution. So we get 1 is equal to E minus, and I guess I'm going to write it as 2 times 4, so I can distribute the 2. And 4 is going to get replaced with B minus 4E. I get 1 is equal to, I'll have negative 2 B's, and then if I distribute the negative 2 here, I'll get 8 E's, plus 1 more E gives me 9 E's, plus negative 2 B's. Now, if you match things up, notice that what we're saying here is that E times 9 plus K, which is negative 2, times B. And so matching things up, we see that D is equal to 9. So now we have the decryption exponent. And I want to point out something. If you're like, well, the decryption exponent and the encryption exponent are the same, I want to make a note here to say that that just worked out by happenstance. It will not always be the case. So here, D is equal to E, which are both 9. This does not generally happen. Otherwise, you can see it's a pretty weak algorithm, right? If the decryption and encryption exponent were the same, it'd be bad news. All right, but for the sake of this argument, we are ready to go. Now, remember, Bill's process here is to take the ciphertext, produce the plain text, and the way you do that is the same, basically, logic of converting from plain text to ciphertext. You take now the cipher, which is 18, raised to the power of D, which is 9, mod 55. All right, so a few lines of work here. First, we'll start with 18 to the first mod 55, which is congruent to 18. 55 doesn't go into 18. 18 squared mod 55. I'm just going to, again, do that here because it's congruent to the remainder of 18 mod 55, which is just 18. So if I do 18 squared, I get 324. 55 goes into that 5 times. 324 minus 5 times 55 comes out to 49. All right, 2 more steps. 18 to the 4th mod 55 is now congruent to the remainder of 8 to the 8 squared mod 55, which is 49. So I have to do 49 squared mod 55. And 49 squared is 2401 divided by 55 is 43. And then 2401 minus 43 times 55 gives us a remainder of 36. One more line, 18 to the 8 mod 55 is congruent to 36 squared mod 55. And 36 squared comes out to 1296. Divided by 55 is 23 point something. So 23 times 55 subtracted from 1296 gives me a remainder of 31. Now, once again, because my power is the same, 18 to the 9th, I'm going to break that up as 18 to the 8th times 18 to the 1st, mod 55. And we know that that's congruent to 18 times 31, mod 55. So 18 times 31 is 558 divided by 55. All right, guess what? That is 558. 55 goes into it 10 times, so that leaves me with the remainder of 8. And so Bill would conclude at this point that, oh, Anne must have sent me P is equal to 8. And we can see, at least for this example, that this process is one-to-one, provided that we follow everything very carefully.